Hi, welcome to section 2 of chapter 13, where we're going to talk about derivatives and integrals of vector functions. So you're probably gonna enjoy this chapter because a lot of this is just calculus 1 material. But what we're doing is we're applying integrals and derivatives to our three-dimensional space and using it in terms of vector functions. So again, the definition of a derivative. Now, the derivative r prime of a vector function r is defined in much the same way as for real valued functions if the limit exists. And so, just like how we had for, a function in two dimensions, so like f prime of x would be the derivative of f of x. It's equal to the limit as the change in x goes to 0 for f of x plus the change in x minus f of x all over the change in x. And just how this gave us the slope, the instantaneous rate of change, what our derivative of our vector function is going to give me a tangent vector. And of course, tangent vector is where we're going to touch our curve at exactly one point. All right, and so that's what we're going to be given when we're finding the derivative of the vector, our vector function, is we're going to be given the tangent vector once we find that. So instead of getting the slope, we're going to get the tangent vector. And here you can see an example of getting the tangent vector. It's just the derivative of r. And so the vector r prime of t is called the tangent vector to the curve defined by r at the point P, provided that r prime of t exists and r prime of t is not the zero vector. Again, that zero's in bold to show that that's the zero vector, not zero, but the zero vector. All right. So the theorem, if we have a vector function, it could be written as f of t, g of t, h of t, or it could be in standard basis form, f of t I plus g of t j plus h of t k, where f, g, and h are differentiable functions. Then we can go ahead and take the derivative of our vector function, and we'll get the tangent vector in either standard basis form or component form. All right, so let's look at example 1. We're given the vector function r of t is equal to t squared or t cubed, and t is equal to 1. So the first thing we want to do is we want to sketch the plane curve with the given vector functions. So the first thing that we want to do is write out our x and y. There's no z. So x equals t squared, y equals t cubed. And if we can, we want to write these in terms of one another. So I know that x cubed is t to the 6, and know that y squared is t to the 6. So I'm going to set x cubed is equal to y squared, and I'm just going to solve for y. And so y is equal to the square root, let me just show the square root of x cubed. All right, again, you could have solved this the other way and said x is equal to the cube root of y squared. And so what we're going to get is this sketch of our curve. All right, because it's square root, all our y values are just going to be positive. And usually when we have x equals the square root, it curves that way. Well, now it's y equals the square root. It's going to curve upwards this way. All right, and I'm going to go ahead and put a few tick marks just to help us out. All right, let's go to 4 for both. All right, so there's A. We sketched the plane curve with the given vector equation. All right. So if I'm going to find r prime of t, then what I want to do is just take the derivative of r. So here's B. R prime of t, it's just the derivative. So derivative of t squared is just 2t. Derivative of t cubed is just 3t squared. So there's my vector function, or my tangent vector. And now for C, what we want to do is we want to sketch the position vector r of t and the tangent vector r prime of t for the given value of t. And so here we have a given value of t, which is 1. So the first thing we'll do is we're going to go ahead and sketch r of 1. So when we do that, we're going to plug in 1 squared 1/3 for x and y. I'm just going to get 1, 1. So let's put C there. So our position vector is going to go there. Now our tangent vector at 1 is, when our function is at 1, this is the tangent vector. So this is what's going to come off of that. And so now we're at 2 times 1, 3 times 1 squared. And we're going to be given 2 and 3. So that means at that point right there, now we're going to also do a vector of x to 2, y to 3. So we're going to go over 2, up 3. And so there's our vector